All right, I'm Lowell Miyagi. That is not me. Okay. Interesting. My background changed. That's okay. So it hides the fact that it says Utah at the top. So my group is a rock and mineral physics group, and we study mechanical and physical properties of rocks and minerals. We are primarily interested in elastic and plastic properties, and in particular, how does rock deformation change the seismic signatures, and can we figure out what the seismic signatures of deformation are? And our primary interest is looking in the interior, mostly the lower mantle and the inner core. And so sort of the first thing we do is we do experiments. So we have to generate high pressures, high temperatures, and it's also tricky because a lot of these phases are not stable to ambient conditions, so we have to study them under high P conditions. So the main workhorse is this thing called the diamond cell. We trap a small sample between the tips of two gem quality diamonds. We can squeeze them to very high pressures. If we want to make things hot, they're optically transparent, so you can shine an infrared laser through. You can cook things. You can also do another kind of heating, where you put a graphite heater around the diamond. This is all in a vacuum box. It turns out diamonds burn if you make them hot enough in air, and they make CO2. So you can go to high pressure, you can deform these things, we can analyze them with X-rays in situ from a particle accelerator. We can also use something called a large volume press. That does larger samples, so for us that's a millimeter or two. This goes to much lower pressure than this guy, and it takes 24 megatons, or meganewtons of power to do that, whereas that it can turn in screws. So we do these deformation experiments, and then we couple that with numerical simulations. So these are some finite element simulations one of my students is doing. And we use that to try and understand the microscopic deformation mechanisms that are occurring and to relate that to our experiments. And if we think we know what's going on that scale, then we try and scale up using simulations. So we'll take a rock, we call them polycrystal plasticity simulations, so rock squishing in simpler terms. We'll take those and we'll couple it to like a geodynamic model, where here we have a slab going down to the core mantle boundary. We'll predict what kind of rock microstructures exist and what the seismic signatures of those are, and then we can compare that to, I didn't have room to put a seismic tomography image, but we'll compare it to something like that. And if we can match it, then we start to think that we can maybe understand how things are flowing in the mantle and to try and image current day mantle convection cycles. The idea is that mantle convection is this engine that drives things like slab subduction, upwellings, and plate tectonics. And so if we can image that, we can gain a better understanding as to why we have things like supercontinent cycles, why we have subduction, why we have earthquakes, why we have mantle volcanoes. So how do I even have a little extra time for the question? Nope.